and today we are to look at to continue on this. That is to continue on the simulation, and the code we developed. This is it. Yeah, so we developed this, and I think what we were left to do was now to proceed with the simulation. But we also said that from this we can't really know whether there are any errors, any syntax errors, and so forth. That's the reason we talked of some of these tools that you can use. But for our class, we said that we'll be using the Icarus Verilog for the simulation part. So that's exactly what we'll proceed on in today's session. So let us make a few notes on that, on the simulation using the Icarus Verilog tool. But of course, you can use any other tool that you may have installed on your part, including the vendor-specific tools. That is if it's from Xilinx, the Vivado, if it's from Intel, Katas Prime, and other related softwares. But we also said that for us to be able to do the simulation, we will need to have what do you call it, the test bench file. So we'll also be developing that, the test bench file, so as to be able to simulate. Okay, so we have said we need a test bench file. Of course, the test bench file itself is a VHDL. So this is a VHDL file, and as such, it will have the same parts like our main file or our main entity file. So it will have the library part. It will also have the entity part, and it will also have the architecture part. So for the library part, as we said, that's more or less a constant. So it will be same as what we have already encountered. But the entity part for a test bench, this one will be empty, because we are not declaring a new circuit. We already have our entity declared in the main file. So for our entity part of our test bench, this one will be empty. And then in the architecture, we are also not defining a new circuit. We are simulating a circuit that was already defined in the architecture of our main file. So for the architecture part of our test bench file, what will be will be instantiating our circuit. So those are the key differences between our main file and the test bench file. The three parts, are there. Library is similar, same, but the entity and architecture are a bit different. The entity, it's empty, and we'll see what we mean by empty. Then the architecture will not be two. It will be instantiating the circuit that we have already designed and defined in our main file. So in short, we are not building a new circuit. We are just instantiating the circuit we have developed and simulating it to see if it works. So in that case, so for the library, that one we have said it will be same as previously. So for the entity, when we talk of it being empty, we will just have the skeleton. So the keyword entity, we give it a name, or whatever name we wish to call it. So user given name is. So remember now, in our main file, we will proceed to put the port of which type and so forth. But for this case, it will be empty. So inside here, instead of having the port things, we just end our entity declaration. So that's what we mean by it being empty. So this is empty. Now, when we come to the architecture, we need to instantiate our circuit that we defined in the main file. So once again, the skeleton of the architecture, we have our keyword architecture. Give it a name, whatever name you want to call it. You can still use the architecture name of the previous of the main file, and maybe with a test bench kind of the suffix. Then it is of which entity. It is of our empty entity that we have just declared above there. So it is of our empty entity there. Then so this is something we have already covered, is, and now this will be the body. The rest of the things will get in there, and of course, finally, we'll need to end. We need to end our we need to end our we need to end our architecture for the test bench. So of course the main things, the main code will be coming in here. This is where we'll be having instantiation of our circuit. And also where we'll be having some code to perform the simulation of the circuit. So in a nutshell, that will be the structure of a VHDL test bench. And because we have an example that we are already working on, we will now proceed to write a test bench for that. And in the process, you should be able to get the flow of developing a test bench as well. So essentially, what are we trying to do? When we talk of developing a test bench, um, remember in okay, somebody wants to join. Okay, so remember in a real life application, of course, our circuit is very simple here, but it could be as complex as you can imagine. But in the real world scenario, the inputs A, B, C, D will be coming from some real world inputs, and the output F will also be, a real world kind of output. So, for example, if you have an FPGA board, you could use switches or buttons to simulate the A, B, C, D, and then the F, the output, you could use maybe an LED to see the output. What combination of A, B, C, D according to this Boolean equation will give either high or low on the output F. You could use an LED. That is, if you have a board. But now, if we are to simulate this in software, and that is what we'll be doing, it means that our input B, C, and D will have to manually put in the zeros, the ones, different combinations of zeros and ones to simulate the inputs A, B, C, and D. And that's where the file, if you recall, one of the objects that the VHDL objects that we covered yesterday. I don't know whether it is in these notes. Yes. Yeah, we add the file. So we said it could be one way of reading the inputs A, B, and C and D maybe in a file and using those to simulate, or you could put in the values of A, B, and C and D in your code explicitly and simulate. So what we'll be doing will be having different combinations of that and seeing what is happening at the output, which should respect this Boolean equation. That is, if the code we have developed, then our output F should respect this Boolean equation. So I think that's good enough. So what we'll be doing now is to develop a test bench file. So we need a new file, and in this case, can save it. So use the same name, and then we can append it with a test bench, a TB, a suffix. Then, of course, it is a VHDL file, and I think that's good enough. Yeah. So as we copy and paste, no big deal. Okay. It seems put it wrong. So this is our example one, test bench. Sorry, my machine is a bit slow. So this is a test bench file. So then once again, we said our entity will be empty. So for simulation, our entity is empty. No, these are just comments. So entity entity, we give it a name, and we can give it whatever name we want. But for consistency, we can use this name, append the test bench suffix, just to, so is, it is empty, so there are no ports we are putting in there, so we just end our example one test bench and a semicolon. So that's it. We are done with those two parts. So of course the main thing is happening in the architecture declaration. The architecture declaration. Yeah, this is of our test bench. So once again, by now you should know the skeleton of an architecture. You start with the keyword architecture. You give it a name, and once again, for consistency, we can just use this name here. Append the test bench. So data of test bench. So it is of which entity? It is of this entity. Copy that, and is, so a lot of other things will go in between there, but finally we'll need to end that architecture with a semicolon. So this is basically the structure of our test bench file. The first two parts are straightforward, so you shouldn't get it wrong. But now the key thing is here now. So how do we proceed? Our let's see our circuit. This is what we are simulating. It has these inputs, the A, B, C, D, and the output F. So when it comes to simulation, we are instantiating something that we have already defined in our main file, and that if we bring up that code that we defined, this one I can put it now in full mode. This is the entity that we are simulating, or rather the circuit that we are simulating. So in a way, we have to create an instance of this circuit in our test bench file. So I will copy this and make the necessary changes so that we do not make a mistake. But the takeaway here is that when we talk of instantiating, we will need to to have this in our architecture, but now instead of it being an entity, we now use a component. So this is the component. So these are now the changes I'm making to that entity that I've just copied. So this is component declaration. So I think it will make sense to, so declaration uh, of the component will be simulating, or declaration of the component to simulate. Of course, these are just comments to guide us on what is happening. And so take note of the changes that I will make to this. In essence, what you'll just be changing is the keyword, entity, and that's it. So from entity to component, the keyword, the component. That's it. That's the only thing that we have to change. And why? Well, it kind of looks a repetition, but that's really how to do the test bench file. So we have the component that we are simulating is this entity here, and that's the reason the name of that component has to match the name of this entity that we declare here. And when we talk of entity, essentially this is the circuit that we are actually building. And in this case, it's just an outline of the circuit, giving the inputs and the outputs. The details or the flesh of the circuit is defined here. So I hope that is clear. So the first thing that you do, remember the library and the entity is straightforward. In test bench file, you shouldn't have a problem with that. The first thing now you need to note when it comes to the architecture, you kind of copy what you have in your entity, in the main file, you put it there, and only change from the keyword entity to component, indicating now that this is the component that we will be simulating. So I think that should be clear enough. So the second thing that we do, once again, if we are to look at the circuit, we have these inputs and the outputs. But as I said, we will be these inputs and so forth. And when it comes to simulation, we will be connecting to these actual inputs of our circuit. So if I'm to, of course the code will be more clear, but what we are saying is that in our simulation, we'll kind of have some test bench. So for clarity, we just indicate them as such. All these are test bench signals. So we can imagine these are storing the inputs that we need to channel to our actual inputs of the circuit. So in a way, we need to have these signal definitions in our test bench file. So we'll do that. It may look a bit confusing, or rather even repetitive, but that's really the structure of the test bench file. So here now we need the signals declaration, and this, as we are seeing, these are for purposes of for simulation. So how do we define or declare signals? From our previous session, we know that we use the keyword signal. As you can see, this is already recognized as a keyword in VHDL, and then these are the signals we need, but of course they have to be different names because they are not the actual ports of the circuit, but these are where now we are bringing in our simulation values. So, but for consistency, we don't want to give them very different names, so we can simply append the TB to these yeah. And then if we look at our notes, okay, we covered signals in the previous session, not yesterday, but nonetheless, if you look at, for example, the variable declaration, because they are more or less the same with the signal declaration, we see the syntax. The key, so there will be the keyword signal, give it a signal name, the signal type, and we can have an initial value. So we can decide that initially our inputs are all at 0. So this is essentially the syntax of, well, for this one it's variable declaration, but it's also more or less the same as that of the signal declaration. So coming back to our code, that is what we need to do. So we have the signal, we have given the signal name, then I'm forgetting what we have just seen. Then we have the colon, the signal type, and then the initial value. So that's exactly what we'll be doing. Colon, the signal type, and we said more often than not, the type that we'll be using in our circuits, it will be of this type, and we give the reason that this is more, it reflects most of the possibilities that can happen in a real world circuit. So it gives 9 possible values. So not just a 0 and a 1, but you can also have things like high impedance, don't care, and many other possible states that a port or a signal may assume in a real world application. So we'll find that most of our ports, signals, well, not variables. Variables now we can have them as integers and so forth. But for our ports mostly, and even this signal, remember this signal is essentially feeding our ports. So in that case, we want to retain that same type. So we said we need a colon and then the signal type. Signal type, standard logic, that's okay. Then what did we need to do after that? Just to make sure that we are following. Anybody? The syntax for that, well, we saw it was a variable declaration, but it's more or less the same as this. So what next? What do I need to type? Yes. Am I on? See, I can't really see this. Let me see if I'm still on. Can you hear me? Okay, then somebody can assist us. What do we need to type here? We just saw that in our notes. I bring back the notes. So here we are. This is the syntax. So signal name, signal type, initial value. So I hope you have seen that. So can somebody guide us? What do I need to type here after the signal type?
You can type colon equals and then initial value.
Okay, yes, thanks. So we have the colon equals and now the initial value. So in our case, the initial value we can have it as low or as 0, and because it's not an integer, it's a bit, it has to be sorry, we need to have the the apostrophe or the yes, I think, and then colon, semicolon, and yeah. So that's our signal declaration. This is for the inputs. So we can just put a comment there. That is for inputs. And then we also have our output. Our output, it is F. So we can append the test bench to that. Then colon, once again, standard logic. And then, well, for this one, we don't need to put an initial value because its initial value will be determined by this, you know, it will be determined by that because this is an output of the Boolean equation whose inputs are this. So for this one, I think we can leave it as such and just put a comment. Let me see if I can zoom out a bit. Yes, we put a comment that this is for the outputs, and I think that's more like it as far as I think. So I hope you followed those steps. First was the component declaration, then the signal declaration, and now the third step is we need to map these signals that we are using to simulate to our actual circuit ports. And in essence, that is now where the actual instantiation will be happening. So we need to do a component instantiation. Yes, component instantiation, and we have two ways of doing this instantiation. I think maybe now it's something we need to capture in our notes. Component instantiation. So this is where we are. So that component instantiation we can do it in two ways. Just try to bring those notes. Well, so apologies, I don't seem to locate those notes on those two ways. I'm looking for the right terms to use, but you can check it up how to do the instantiation. Um, but basically, we can do it two ways, and we have the right terms or how we refer to this. Those are the terms I was trying to get. But the bottom line is that one of the ways is we can do them. We can do the instantiation by I will say positional. Uh, this is not the right term as it should be called, but for purposes of the session, I will use this positional instantiation. And in our example, we probably see that. But here we are saying that, remember, we have our signals, our test bench signals, and our actual ports and names. And here, when we talk of position instantiation, we will just be arranging our our signals in the same sequence as our ports, and as such the simulator or VHDL will be able to map, will be able to do the port mapping, so component instantiation and port mapping. So it will be able to associate that sequence with the actual port. So let's say we have something of this sort, um, B, TB, C, TB, and so forth. And in our actual port, the sequence is as follows. So in this case, because the sequence is is similar, is the same, then A TB will be mapped to A, B TB will be mapped to B, C TB will be mapped to C. So this is based on the position. And I have seen there is the name given to this. I don't remember that, but what this is actually what happens. Then the other one, the other way, once again I can't remember the term to use here, but this one is I will say explicit port mapping. So you make it clear to the simulator or to the to VHDL that I am mapping ATB2 to A, or the other way around. I'm mapping BTB to. You can even map it to CP, because these have no relationship to this. These are just for your own consumption. But you could map anything to anything. You could map something you have called D test bench to B. Of course that would be confusing even to you as the designer, but you could do that. So there are those two ways: positional and explicitly mapping that. But you can check out this and see the right terms to use for those two ways of doing it. But let's go back to our code, our test bench file that we were working on. So we have the component instantiation, and I will also say component instantiation and port mapping. And the syntax for this is, remember, you can instantiate your circuit. Okay, this component instantiation and port mapping is actually what you would expect in our structural, in the structural design style. Maybe just to bring that back up. Once again, it's not in yesterday's notes, but we talked about the various design styles, and one of them was the structural design style, where we said you can subdivide your circuit into various components, and then we instantiate those components in one file. And this is exactly what will be happening in such a situation. And you'll find that, for example, let's say you have a complex circuit, and there is one sub-circuit that is appearing in so many instances. So you can instantiate a component more than one time, depending on exactly how many instances of that component you need to instantiate. Let's say your circuit is made up of just logic gates, the AND gates, the OR gates, all over the place, and for some reason you have subdivided that circuit just based on a single logic gate. So you'll find that maybe in your circuit you have like 10 AND gates or 20 NOR gates. You can instantiate those NOR gates 20 times. So you can create 20 instances of a single NOR gate, so that in total you actually have 20 NOR gates. So in that case, you need to give a name to each and every one of those instances. So if you have like 10 NOR gates, and you have to instantiate 10 10 of them. So maybe the first one you'll say NOR 1, NOR 10, NOR 2, all the way to 10. So you give each them a name, an instance name. So the same thing here, even in our test bench file, we have to give a name to the instance. So in this case, because this is a test bench file, we are only instantiating our component once, because that is the only circuit we are simulating in this particular test bench. So I can decide to call this test bench one, our instance, as a test bench one, and then we have the colon, and what are we instantiating? It is our this the example one, which is our circuit. So this is what we are instantiating. So in our, can copy that, in our, so we are instantiating an instance, giving it a name, a test bench one, and it is an instance of example one. And now, so that is the part of component instantiation, but now we need to map. We need to map our signal, these ones, to the actual ports. So that's the next. So we need to do the port mapping, and this is the syntax for that. So here we use the explicit mapping, where now we are mapping, this is the syntax, we are mapping explicitly our ports as such. So I think I can just copy that. The last one, we don't need a comma. So the next one will be B of C, we have D, and we have the output F. So we are mapping our actual ports to our simulation signals, D, and then F. So that's it. So you can see this. Of course, the port is something we have already encountered, and it's a keyword, hence it's highlighted. And also the mapping, it's a keyword in VHDL. So this map, it's known what you are trying to do. You are trying to map some ports to some signals. So there is some components that you are instantiating, and you need to map those ports and signals, and this is exactly what is happening. So this one, we are doing that explicit kind of mapping, which I see there is a term given to that. I can't remember. You could also do it a different way. That is by positional kind of mapping, but you can check those up. So far, this should be clear to you that so far we have the 3 steps. As far as the test bench is concerned, those will be the main 3 steps you'll be following. The declaration of the component to simulate, and remember what we did. We just came here in our entity, copied what we have there, put it here, and changed the keyword component, and was it. Then the signals declaration. So we need some signals for simulating our ports, and basically they will be these ports, but we need to give them a different name because because we need them to be of different names. But for our convenience, we just append this test bench to them, and that's it. Then the third step was to now instantiate and do the port mapping. So we have instantiated our component. Our component was example 1. So we instantiate that and we give it a name. We could instantiate this again if now it was some structural design style. We and we were instantiating very many instances of the same kind of circuit. We could now have many other instances of the same, but because for us this is a test bench and we are only simulating this particular circuit, we only need to instantiate it once, but we need to create a name, and then we need to do the port mapping, which is given here. And as I said, of course, this A you can map it to C test bench, and that is where your value of A will be obtained from. But of course, that will be confusing to you. In other words, I'm saying you can give these the names that you want. These are user defined names. But we have said for our convenience and clarity, code clarity, we use the same port name and just append that. So those are the 3 steps that you definitely need to take in the test bench file. So if you miss any one of them, then you are doing something wrong. So finally, remember, so far we have not done the actual simulation. So now finally, we need to do the simulation. So here we can talk of. So when we talk of simulation, it means we need to generate some values that will be into A, B, C, D, and observing what is happening at our output F. So there is some generation of the stimulus, it's the name simulation, and now, so we have a stimulus, sorry, we have a stimulus generation. So we need to have a way of generating values for our signals. Remember, these are the signals where we'll be generating our values, and because they are already mapped to our ports and our circuit is already defined here, then everything else should proceed automatically. So remember, our signal, this what we are using to simulate, we declared them as signals. And remember what we talked about, signals versus variables. And just to make sure that we are on the page, we are on the same page, can somebody remind us of any difference between a signal and a variable? Anybody? Signal and variable? Any difference? Sorry, you can remind us of that.
For signal, use assignment user less than or equal to operator. Then in variable,
Well, that is correct. In a variable, we'll actually use a colon equals to, right? Not just equals to. We'll use this in in a variable, we'll use this in our variable assignment, whereas in signal assignment, we'll use the less than equals to operator. That is one difference. But there is also another one that I was looking for. Somebody else. In fact, I think we gave two differences. So what was the other difference? So thank you. Is it Emmanuel? Yeah. Somebody else. What was the other difference between a signal and a variable, apart from the operator that we use for assignment?
The signal is only used in the architecture. Okay, it's declared in the architecture process or in the port, but the variable only in the process.
Well, that is correct, but actually I don't think I mentioned that in class for simplicity. There is one key aspect of a signal that you are not mentioning.
A signal you can declare after a certain period of time.
Yes, very correct. So for a signal, it doesn't take effect immediately. So it has an aspect of time. For variables, we said once you do the assignment, it takes effect immediately. But a signal has the effect, has a time component to it. And that's the reason we use it for this simulation. We don't use a variable for this simulation because now with the signal, remember we want to see the behavior of our circuit over a period of time. So at some point, we give A maybe a value of 0 or 1, B another value, C another value, D another value. Of course, it's either 0 or 1. And then after some point, after some time, we change those values and see the changes in F. So we need a data type that we can manipulate on the basis of time. We can explicitly give some time to it that, at this time, you'll assume this value and so forth. So that's the reason we use a signal here instead of a variable. So when it comes to the stimulus generation, that is where we need to bring in that aspect of time. So once again, the syntax for this part is as follows. We can choose to give a name to this process that we are about to put here, and we can call it stimulus. We can call it stimulus. That is a process. And so this is now the block or the stimulus generation block. So the skeleton for this. So this is where I think we can put a space there for clarity. So this is the block in which we'll be generating the values of our signals, and yeah, so we can do exactly that. Remember, it is our only the inputs that we need to generate values for. So there are a number of concepts that now are coming into play. Signal assignment, you have to remember the you have to remember the operator that we need to use in signal assignment, and Emmanuel gave us that we need to use the less than, equals to. So we use less than, equals to. So this one now, it is up to you which value do you want to give at what point and so forth. So of course we can decide to have like a truth table. You start with 0000, then 0001, 0010, and so forth. You can choose whichever way you wish to do that. So for the first case, we can start with all of them being a 0, because we terminate that the semicolon. So I will just copy this and copy that. So we are starting with all our inputs being at 000. Now we bring in the aspect of time. So I can copy all this. I think let me minimize this. I can copy all these and just I don't want to do many, so I think we can stop there. And now whatever we'll be doing here is arbitrary. You can choose whatever values you want to change and so forth. Yeah, this is now completely arbitrary. Remember, the key point is just to simulate different values of your inputs and see whether your output is changing accordingly. Yeah, so I think those are enough. We can, okay, maybe we need to put our maybe a 1 somewhere here at least. Also maybe a 1 here. Bit complex, but if you have been following, the key thing is to understand the steps that you need to follow. First, library entity is empty. Yeah, that should be straightforward. Then the next part is architecture part. And in the architecture, we kind of have 4 steps. 1 is the component declaration. 2 is the signals declaration. Then the component instantiation and port mapping. And finally, the generation of your stimulus, or simply the simulation now. And that's it. So if you remember those 4 steps, then you should be okay. The key thing maybe to note here will be now the assignment, the operators that you need to use. For example, the port mapping, you can see the operator that we are using, equals, greater than, that's the operator that indicates the port mapping, the explicit port mapping. When it comes to signal assignment, we use the less than, equals to operator. Yeah, then I think by and large, if you grasp those particular steps, you should be okay. Yeah. and still you recall our main circuit, which you can see how simple this one is compared to the test bench. And mind you, the test bench in actual design is optional. If I'm sure this is my circuit and I've designed it well, I can go straight ahead to implement it. If I'm using an FPGA board, I can just compile this and have it running on the FPGA. I don't need to write this to do the test bench. The test bench is just for simulation. So of course, if you are confident with your circuit design and you feel you don't need to simulate it, you don't need to write a test bench, right? So a test bench is not synthesizable. You cannot implement a test bench in hardware. This is simply for simulating your top design to see if it is okay, and that will allow you to now proceed with the implementation. And you may ask, why do I have to write all this if I can just compile this, put it on my target board, and I will be able to see whether it is working or it's not working? This is a very simple design, and you can proceed just to compile and have it run on the FPGA if you are using an FPGA as the target. But in some complex as the complexity of your circuit increases, you realize that also now, depending on your machine, to actually compile. Now we are talking of things like on Vivado and Catus Prime, where now you're actually doing proper FPGA development, moving from this code to compiling it and generating a file that can run on the FPGA. It can take probably even more than 30 minutes or an hour, depending on the complexity of that design. And you can imagine waiting for an hour for something to compile, and there was an error that you could have easily picked out if you just developed a simulation file and did the simulation, which will take less than 2 minutes. The simulation itself is very fast because the code doesn't need to go through the whole process that is needed for something that actually runs on the hardware. So that's the reason you want to simulate. You want to cut on time. You don't want to spend an hour waiting for something to compile, only for you to realize there was an error that you could have just picked if you had used simulation. So that's really why it is good practice to simulate your circuit. But nonetheless, I think we have gotten a taste of the two worlds, our circuit design and our top design, and how we also develop a test bench for the same. Up to this point, we really don't know whether these are correct or we have errors, because I also don't know. You may have missed a colon, you may have introduced a colon where it's not needed, and so forth, semicolon, and so forth. So up to now, we really don't know the correctness of our code, and that's now the next step that we need to take. In fact, I wanted us to take a break so that we can come back and do the simulation. But Eric, you raised your hand.
Yeah, I just wanted to ask you about the stimulus process.
Yes.
Scroll down to the stimulus process. Like they have just seen that you provided a time delay between a bunch of all the input signals.
Yes.
Whether we should just have a time delay between an individual input signal.
So, sorry, come up again.
I was just asking about the time delay you provided for all the input signals, and it seems to be something repetitive. And I don't know whether you should have a time delay for specific input signal for signal simulation.
Okay. You are saying we can have a time delay maybe for each of these signals?
Yes, because like it's as if you just repeated the entire the same line, and the time delays for all the input signals.
Yes, and yeah, you are correct. And as I said, now when it comes to this simulation, it is up to you. How do you want to change your inputs? Somebody will decide. I first want to change the A input, leave the rest as they are, and see the change. Then maybe I move to the next one. Somebody else will decide, at every instance I want to change all of them at the same time, and so forth. So this is it's completely, you know, you can do this in very different ways. Somebody can do that, and you can bring this there, then move to maybe this and the delay and so forth. Yeah, so it's all that is correct and up to you. But for purposes of this session, I just put them, together. As you can see, for example, after this delay, the A input is not changing. In that case, we could have as well just have that same effect. Yeah, but I think for just to be able to see things at a glance, I just retain everything at each of the steps, so that at least at every glance you can see what is the value of A, what is the value of B, C, and D. But this is completely, um, uh, it's variable. It depends on how you want to do it. I hope that answers you.
It's okay, thank you.
Yeah, so I think we can take a short break, 5 minutes, and then we come back and proceed to compiling this, simulating, and maybe we can end the session there. Okay, we can continue. So I hope you managed to get the tool that we talked about, and that Icarus Verilog will be able to help us in this simulation, and a few commands that we'll be using. You can check these online. You can check the this for VHDL, what do you call it, simulation. You can check it up on this site. Of course, if you just search for it, you will also be able to get the same site or another site. So this will give you the PHDL simulator. So the main commands that we'll be using, one is the analysis command. Analysis command, and as the name suggests, this is simply to analyze your file, to compile your file and see if there are any errors, syntax errors or otherwise. So that is the first command that you want to use. So this analysis command, it compiles one or more files. You'll get all these online in that site or any other site that is relevant. So this compiles one or more files and it creates an object file for each source file. So we will wish to compile our source files just to make sure that they are correct, and the command itself. So for this, you'll be starting with the GHDL, kind of a command or a pointer that you are doing VHDL simulation. Then for analysis command, we use that the A switch, and then we have the name of our files. That's basically it. The second command that we need to use is the elaboration command. Elaboration command. And this command, it creates an executable. It creates an executable containing code of VHDL sources. And this is on a Linux-based machine, so it creates an executable containing code of the VHDL sources, and this command, it is used on on an entity, on an entity unit. We'll see what that means. So the command itself, so it's GHDL. We use the switch E to illustrate an operation, and then we have the primary unit, and we have the primary unit, and also secondary unit if necessary. So for this primary unit is what we are saying, this needs to be the name of an entity. So not a file, but the circuit we are actually simulating. And then finally, the other main command that you need to use is the run command. And this as the name suggests, this runs the simulation. It's you can see this. It launches the simulation, and the command itself is GHDL. And for this, we use the R switch to illustrate the run command. And then we have the primary unit that we are simulating. So all these will be clear when we run the example. So you'll be able to look at these in more details in your free time. But these are the three main commands that we'll be using to work on these examples. So we have our top file, the synthesizable file, and then we have the simulation file or the test bench. So those are the files we'll be working on. And so I've just opened a terminal to the location of the files. So let me know how visible is this? Is it clear enough? Somebody to confirm. Is it visible enough?
Yes.
Okay, perfect. So as you can see, we have our two files. We have our main file, and we have the test bench, the test bench file. So those are the two files that we'll be working with, and the commands that we have just given. Unfortunately, if I minimize this, then it will not be that visible. But the commands that we will be using, we have the analysis command, and this is simply to analyze and compile our files to see whether there is any error, and that's exactly what we'll be doing. So this is the syntax, GHDL-A, then our file name, and we should be good to go. So we have G, and this, of course, this one will run if Icarus is you have kind of installed it. I don't know even if installation is the right term. I think it's just a file you run and well, it installs. So if you run this command, I verify yeah, if you run this and it gives you what we are seeing here, then it means you have that simulator running on your machine, and therefore you should be able to do the rest of the things we are about to do. So now we can proceed with the simulation. So GHDL analysis. So we want to first we compile our top file, copy, and see if there is any errors. Okay, so if we don't see an error, then it means our file is is okay syntax wise. And maybe if we doubt that, we can actually intentionally introduce an error and see. Let's remove this semicolon there, and I save that file and go back to our simulator. We complete it's able to pick out that it was expecting a semicolon at the end of the signal assignment. Are these things legible on your side? Can you
Yes.
see that? Okay, perfect. Yeah. So at least we have verified that this our simulator is actually behaving as it should. So we rectify that mistake, save the file, and yeah, and run the simulation again. So for sure, our top file syntax wise is correct. Then the next thing we want to do is to analyze or compile our test bench file, because also that one we need to check, have we got everything correct? And our test bench file is this one, that one up there. That is what we have down there. So we run that and see. Oh, and indeed you can see we have quite a number of errors. Now these were not intentional errors. So to actually study this, line 5, end must be followed by component. Then object class keyword such as variable is expected. Then begin is expected instead of stimulus. Okay, those are some line 5. End must be followed by component. So we bring up that. Now this is on the bench. No, actually it was line 19. So component example 1 is put. So I think this one if we look at the error, and actually I think I know what's happening. So if we look at this error, it's saying that end must be followed by component, and actually that is it's correct. That's another thing that we actually needed to change here. When it comes to this end, we actually end the component. So we, instead of a given name, we actually end the component as is. I think whether you use capital or small letter, that's okay. So as far as that error is concerned, I think it should go. So we have end component. So I've saved that. We can recompile and see whether that error is gone. So at least the first error is gone. So please take note of that. That in the test bench, remember where we copied the entity from the top file, we brought it into the test bench. We changed the keyword entity to component. We also need to change when it comes to the end, we end the component, not the entity name. So please take note of that. Then there is this other error, line 26. The object class keyword, such as a variable, is expected. Then test bench 1, example 1, bottom. I'm not sure what that implies. Use our code, line 26. So component instantiation and port mapping. I'm not sure which error. Don't seem to notice any error here, and I'm wondering whether it's yes, actually I think we should read that error in we should read this error in conjunction with this as well. So begin is expected instead of stimulus. So actually, I think maybe that is the same error that is giving rise to the first one. And indeed, we need to remember these were declarations in our architecture. So if we come to our example here, you can note this begin. We have the architecture is begin and we end it, right? So the key structure of the skeleton of an architecture is as such. So it has to have a begin and end. Begin for the architecture. Yeah, our architecture is here, but we have no begin. We only have a begin and end for the process, and we're also ending our architecture, but we didn't have a begin. So that begin for the architecture should come after these two declarations, the component and the signal declaration. So we should now begin. We should begin our architecture, and we can note this is the beginning of the architecture, part. So that is you please take note of that. So this the begin here is what is actually being, we are ending there. So I think with those, if we save, it's more or less should be okay. Yeah, so you can see our, just to confirm that, we have no more errors. So that means our test bench, syntax wise, is good. Our top file, our entity file, is also okay. No errors. So please make note of those changes that we have made. Those errors, especially here. Yeah, it's very possible, of course, to make these errors. So the architecture begin needs to be there, and it comes after we have made these declarations. Yeah, and I think which was the other error? Oh yes, the component instance, the component declaration. We are ending the component, not the component name. So those, I think, were the two errors we made there, and we have corrected that. So you can see our very lightweight simulator is actually able to pick out those mistakes. So the next thing we needed to do was to do the elaboration. This is the command used on an entity unit. So when we talk of an entity, if you look at our analysis command, we were actually using the file names. Example one, test bench, example one, .vhdl. So we were using the file names. But now when it comes to elaboration, we actually use the unit, the entity unit name, and that's exactly what we need to use. So we come to our test bench file, and what was our entity name? It is example one TB. Yeah, this is our entity name. So we have to copy that. We come here, GHDL, we elaborate. We elaborate our entity. I think the mistake there. Yeah, so that is it. We, as far as that command is concerned, we are okay. Remember, we are doing simulation, and we are using our test bench file to do the simulation, and therefore, when it comes now to those two commands, the elaboration command and the run command, will actually be working with the test bench file, because our top file is actually referenced or instantiated from our test bench file. So we only use the top file, our top design file, in the run command, and that is simply to compile it to make sure that it is, it's correct, there are no errors. And then for the other two commands, we use our test bench file, because that is what we are actually simulating. So in the first instance, the elaboration command, we elaborate this entity name given in the test bench file. Then in the run command, we now run our test bench file, which we actually run our entity, which is defined in the test bench file. So we still need this. So coming back here, So the next command is run. That's a run command, and we are running that particular entity which is defined in the test bench file. Now there is one more thing that we'll need to do here. This particular simulator that we are using is very lightweight. It actually doesn't have a graphical user interface. So we need to store the values it generates during the simulation somewhere, and then we'll use a graphical software to view those waveforms. So we need to dump the values that the simulation will generate somewhere, and then from that file we'll be able to view graphically using a graphical interface. Of course, if you are using Vivado, you are using other vendor software tools, everything is inbuilt, so you will be able to view your waveforms from that single software. But for this one, it's very lightweight. It will just do the simulation in the background, but it has no graphical user interface for us to view the waveforms. So we need to give a command, and that is the variable change dump file. We need to specify where all the values generated during this simulation, where they need to be stored. And for that, we continue to just, for a good practice, to just use the same name, but now it has the extension .vcd. So we are running our simulation entity and storing the values generated in this file. So this is a new file that we are creating, and this VCD stands for value change dump. We are dumping all the values generated in that file. So we run that. If there are no errors, it will terminate successfully. It's still running. I hope this is still visible on your side. Is it visible?
Yes.
Okay, thanks. Yeah, so it's still running. I don't know why it's taking that long. Essentially, it really shouldn't take that long. I think that there is something wrong there. It should not take that long. It seems to be running definitely. So I think there is something you might have missed. Trying to see how to. Well, let's see whether we have. So if we have a new file created, I'm not very sure whether we have managed to. think let's remove these files. And let's have a look at our simulation. I think we may need to add a weight there. Let me just see whether this will. So of course we have changed the test bench file. So we once again we need to recompile it. So we need to run the analysis on our test bench, and then we need to elaborate our test bench entity. Line 27. Have we done any alterations on line 27? Okay. Okay. Let's start by compiling our top design file. So let's start by compiling, and then we compile our test bench, and we elaborate. Yeah, okay. And it means you have to, if you change the test bench file, you also need to once again recompile the top file and then the test bench file. Then you elaborate the entity in the test bench, and then we run. Our simulation. So we run this. Yes. Yeah. So we have our VCD file where now all our simulation values have been simulated and now have been stored, and now we can use a graphical interface to actually view the waveforms in that particular file. And for that, I will be using the GTK wave, which is also a lightweight graphical user interface to view the contents of that file. Well, hopefully it will open. Okay. So here we have that. These are very small. Can you see anything? Can you see this? Our instance here, test bench 1. Yes, and then we have our signals, the A, B, C, D, and F. So now this may not be that visible on your side, but I want to fit. If you see, these are very, so I want to fit that into into this window. I'm trying to see how we used to do that. Yes. So at least, yeah, so you can see at least now it is in the time scales that we anticipate, nanoseconds. And yeah, so this is the waveform. Unfortunately, there is no way I can, I don't know what you are seeing on your side because let me, yeah, I think you can actually see. So yeah, so here we are, we have done our simulation. So if I put my cursor there, I'm able to read the values of our inputs and outputs. So here we have currently 0, 0, 0, and our output is 0. If I come here, I put the cursor here, I can see that our A input is 0, B is 1, C is 0, D is 1, and that gives us 1. But actually, we didn't even try to analyze what we expect. Of course, if you are simulating, you need to have an idea of what you are expecting. So what was this was our circuit. This was our circuit, and this was the Boolean equation. So let me just so what are we actually simulating? We have F is this our the equation that we actually have? Yes, right? This is what we have. So we can very quickly try and see what we expect. So we have the case where 0, 0. Let's see what we have in our waveform. The other one is 0, 1, 0, 1. So 0, 1, 0, 1, 0, 1, 0, 1. And of course, these are coming from what we put in our stimulus. You can see 0, 1, 0, 1, right? The next one is 1, 0, 0, 0. So in our, then we have 1, 0, 0, 0. Then the next one is 0, 0, 1, 0. So 0, 0, 1, 0. 0, 0, 1, 0. 0, 0, 1, 0. I think those are enough. So can somebody give us what we expect the output for these combinations of inputs? So when it's 0, 0, can we plug it in here and see? So if it's 0, so A is 0, regardless of what B will be, this will give us a, this term here will give us a, and it will give us A is 0. So what will that
0, 0.
Yes, it will give us a 0, then or, so these are 0, 0, so these ones will be, they will give us a 1, right? Because it will be 1 and 1, so that is a 1. So 0 or 1 is 1, but then we invert it, or we complement it, so it becomes a 0, right? So is that correct?
Yes.
Okay, so using the same analysis, can somebody give us the output for the second? So we have 0, 1. So this term will be, so we are saying 0, 1. This term becomes 0, right? Yes? 0 and 0. Yeah, yeah. Or then C is 0, D is 1. So this become So also this becomes 0, right? The end result there is a 0. So 0 or 0 becomes a 0, but then we invert it, becomes 1, right? Is that correct? Can somebody verify that?
Yes.
Yes. So I think up to there we are in agreement. Then we proceed to the other option, 1, 0. So here is a 1, 0. So this also becomes a 0 finally, right? Yeah. Then or 0, 0, 0, 0. So this becomes so it becomes a 1. The end is a 1 inverted, which becomes a 0. Is that correct? Yes, somebody verify that.
Yes.
Okay, thanks. Then our final is 0, 0, 0, 0. So this also becomes a 0 finally. Then or 1, 0. This also in a way becomes 0 finally, right? Then we have 0 inverted, which becomes a 1. Is that correct?
Yes.
Okay, so at least we have an idea of what we are expecting as our output. So we have an idea that we'll have 0, 1, 0, 1, right? And we just did this randomly. So and we can see our output is kind of alternating 0, 1, 0, 1. So let's go to our simulation. So we are starting with please read the values on our signal values here, because these give us what we're expecting. So 0, 0, 0, it gives us a 0. The next one, it gives us an output of 1. I hope you can see that. We proceed, it goes back to 0. We proceed, it goes back to 1. And that follows what we have already seen. So it's alternating 0, 1, 0, 1. The next one, it remains as 1. We are not yet done that. We can actually verify that very quickly from our code. That was 1, 1, 0, 1. 1, 1, 0, 1. 1, 1, 0, 1. So our next 1, 1, 0, 1. Can we verify what this gives us? So we are saying this is 1, 1. So this becomes what finally? It becomes a 0 finally, right? Or the other one is 0, 1. This also finally becomes a 0, right? So this becomes a 0. We invert that, it becomes a 1. Is that correct?
Yes.
Yes. Sorry?
Yeah, it is.
It is, yeah. So I think then that gives us the confidence to say that our simulation is actually okay. And not only our simulation, it means now our circuit design is actually correct. What we remember, what we were simulating is really this file here. We wanted to see whether our code here actually gives us the circuit that we were trying to design, and our simulation shows that indeed we are getting the output we expected. So because of time, I think this is a good place to stop. Of course, if you now have installed Viva or other softwares, if you are keen, you see this as it's not vendor dependent. This is a generic this is a generic VHDL code. You could implement it in whatever device, whether it is a Xilinx device, whether it is Altera or Intel FPGA, you could implement it there. What now you'll just need to change is to map your ABCD ports to some specific pins on that particular FPGA, and you'll be good to go. That's the only additional thing you'll have to do to this code, to map the ABCD to some specific pins on that particular FPGA, and that will be good enough. So, in the interest of time, I think we'll stop there. But from my end, I think we have covered as much as we could with VHDL, and yeah, we are now better off than when we began. At least you have the full understanding of what it takes to do some VHDL circuit design. And remember, this is hardware description language. We could have used Verilog to achieve the same results, but we chose to use VHDL. Of course, there is a lot more that you can learn, which you are free to do, and also how to transition this to an actual FPGA. As I've said, there is very little that you need to add, just to map the inputs to actual pins on the FPGA. That's all you need to do, which I think if you look at a few videos, maybe online, you should be able to do that. So the next time we meet, we'll now proceed to the other parts that we are done with the FPGA part of it. So I think unless there is any query question, I will share these notes with you via the same platform, and then we will actually have our CAT on Thursday. In any case, that's really the CAT week. So kindly prepare such that on Thursday, during our class time, 2 to 3 p.m., we will have our CAT, just 1 hour CAT. I think we can leave it at that, unless there is any query. Is the class rep with us? Just to make sure that communication is taken.
Yes, I'm here, sir.
Okay, thank you. So please note on that CAT.
Excuse, I just wanted to ask about the scope of the CAT, whether what we've covered today and other things related to the HDL programming will be part of the CAT, just to know, just guide our revision. Yeah.
Yeah, well, I think the scope of the CAT is actually up to today. So whatever it is we have covered so far is eligible to be in the CAT. Also for your own sake, as far as preparing for the exam is concerned, you need to cover at least up to today's work when you prepare for the CAT. Yes, so the scope includes up to where? Up to here. I hope that's clear.
Yeah, it's clear, sir, but we can it would be better if you would have spared us from this, because now it's on 1 week notice, and the coding part, maybe it could be challenging. We'll prepare that for exam.
Spared you from what? The CAT?
Not really. The last part that we've been covering yesterday and today.
No, but today is on Friday. You have okay. I will not bring the VHDL, and I don't think that is helpful to you. But if you have requested so, we will not cover VHDL in the CAT.
Okay, thank you.
Okay.
Highly obliged, sir.
Okay, then I think we leave it at that. We'll meet next week, and enjoy your